there's two ways that we can set out the problem, and you'll see both ways used in different situations. So I want to show you both ways. The first one I'm going to show you is probably the way I would do it, because that's the way I'm used to doing it in the past. But then we'll look at the way that may well be done in certain engineering scenarios. So the first thing we do, so this is method one, if you like. So first method. What we do is we add up all the clockwise moments, and then we add up all the anti-clockwise moments, and then we put them equal to each other. So I will label, first of all, I'm going to do the clockwise moments. But the clockwise moments and the anti-clockwise moments that we're going to work out are all about a pivot. So the first thing to do is to decide which end we're going to call the pivot. So what we do is we say, I'm going to call, say, let's label this end A and this end B. So let's say I'm going to call this end A the pivot to start off with. So it's pivoted at A. That means I can then calculate what this reaction force is at B using the method we just looked at the other screen. Once we've done that, we then switch our idea and make the pivot at point B, and then we can find the reaction force at point A. So what we do is we just assign the pivot to various points on the lever, and then find moments, clockwise and anti-clockwise moments about that point. So method one, clockwise moments about A. So let's subscript A means we're assuming the pivot's at A. So now we take each of these forces that are acting on the beam and ask ourselves, is it going clockwise or anti-clockwise? Well, this first force, the 20 Newton force, is trying to pull it round clockwise. So that's, if it was acting on its own, it would be going clockwise. So this is contributing to the clockwise moments. So that's going to be 20 newtons, which is the force, multiplied by the distance of that force from the pivot. So if this distance here is 1 meter and that's another meter is 2, 5 meters altogether, this distance here must be 3 meters. Okay, so times 3 meters. That's the contribution for the 20 Newton force, if you like, if you want to label that. That's a 20 Newton force. That's 3. Okay, plus, now we're going to do the contribution for the 10 Newton force. And what's that going to be? 10 multiplied by 4. Right. And there are no other forces pulling the thing round clockwise, so that will be the sum of all the clockwise moments, which equals 60 plus 40, which is 100 Newton meters. And then we find the anti-clockwise moments about A. So anti-clockwise moments about A equal, right, if I just look at this one, because we'll look at this together. So what's the anti-clockwise moment about A? The only force that's acting anti-clockwise is the reaction force at B. So we'd label that RB for the reaction force at B. So that will be RB times the distance, which is the full length of the beam, 5 meters. So RB times 5, which is 5 RB. And then, being good engineers, we would state the rule that we're then going to apply next. In a balanced situation, clockwise moments, anti-clockwise moments equal clockwise moments. So we'd state that, and we'd say, therefore, RB, 5 RB, must equal 100. And RB equals 20 newtons. So that's the reaction force at B. So what load is this support B taking? A force of 20 newtons. So I need to make sure that my support can take a load of 20 newtons. Now, I want you to assume the pivot is at B and work out the reaction force at A using exactly the same method. Beware when you do it that you consider clockwise and anti-clockwise moments correctly. This time, if I consider it pivoted at B, then this 10 Newton force is going to try and turn it round anti-clockwise, isn't it? So what I want you to do is a similar method, add up all the clockwise moments and the anti-clockwise moments, and then try and calculate for me the reaction at A. So hopefully you got that the clockwise moments is just the reaction at A times 5 meters, and that the anti-clockwise moments this time will be 10 newtons times 1 meter, which is the distance from this pivot at B, plus 20 newtons times by that distance, which is 2 meters. Okay? And then you get 50 newton meters altogether. So the next step, put them equal to each other. So anti-clockwise moments equals clockwise moments, and therefore 5RA equals 50. So therefore RA equals 10 newtons. And if we go back to our original diagram, we can now write that RA is 10 newtons. Now if you look at this diagram, you can see that the total upward force is 20 plus 10 is 30 newtons, and the total downward force is 20 plus 10 is 30 newtons. Rule 1 is confirmed. Okay? Total downward force equals total upward force. You could have argued that once I've got the reaction force at B, which is 20 newtons, why not just subtract that from 30 to get this as 10? Okay? I would say that the danger with that is if you get this wrong, then you're going to get that wrong too, aren't you? And if you're doing a real problem and you want to know this and you haven't got a lecture in front of you to say yes, that's right or wrong, I would actually use rule 1 as a check. So I'd do exactly what you've done, and then I would, now that I've got my two answers and total up equals total down, I can be fairly confident I've done it correctly. So don't automatically just use rule 1 for the other one, because that could be used to check you've not made a mistake. Okay? So that's quite straightforward, isn't it? Okay? There's method 2 that I want to show you. Let's put that underneath. I'm not going to do the whole thing, so this is method 2. It really just comes down to convention. If we look at this beam, we could say that the sum of the moments is 0. So what that's saying is clockwise moments equals anti-clockwise moments. So in very short mathematical statement, we're saying that the sum of the clockwise moments and the sum of the anti-clockwise moments together must equal 0. The sum of the moments must be 0 when it's balanced. So we'd find the sum of the moments about A must be 0. So we would assume the pivot was at A, and we'd say, in that case, we're going to talk about, say, anti-clockwise moments being positive. So we put a little arrow around there saying, right, I'm going to treat all anti-clockwise moments as positive, therefore clockwise moments must be negative. So then I'd go through the same problem. I'd say, so therefore clockwise moments are going to be treated as negative. So I'm going to start off by saying anti-clockwise moments, which is RA, RB, sorry, times, so it's 20 newtons times 5 meters gives me my clockwise moments. So I'm going to say R at B times 5, so 5RB, minus, because now I'm going clockwise, 10 times, whatever it was, 10 times 20 times 3 meters, minus 10 times 4 meters equals 0. So I'm doing the same problem, but I'm using a different approach. So then I'd say 5RB minus 60 minus 40 is minus 100 equals 0. And then I've got a little equation to solve, and I'd actually end up adding 100 to both sides to say that 5RB equals 100 and RB is 20 newtons. So in other words, I'll end up with exactly the same answer. I've just used a different approach to the problem by saying that the sum of the moments equals 0.